All right, let's look at the vector space chapter, and here we'll look at some vector space properties. These properties are all variations of properties that you've seen before, and they're also properties that you know are valid for column vectors. So let's take a look at some of these. This one, additive closure, just says the sum of vectors is a vector. So as we go through these properties, you should be relating these, say, to C3 three-dimensional vectors. That's a good example to think about. So certainly the sum of three-dimensional vectors is a three-dimensional vector. So scalar closure, the scalar multiple of a vector is a vector. Commutativity, the sum of vectors can be done in either order. Associativity, the sum of vectors can be rearranged in the associative way. There is a zero vector that adds to any other vector, gives it the same vector. There is an additive inverse vector, here, let me get this out of the way, that we call minus u, which is suggestive. In fact, minus u turns out to be minus 1 times u, where minus 1 is the scalar minus 1. But we say there's an additive inverse vector such that u plus minus u equals 0. Let's go down here. Scalar multiplicative associative, it means you can multiply a vector, then multiply by another constant. That's the same thing as multiplying the two constants together first, and then multiplying the total by the vector. Distributivity over vector addition, I can add two vectors and multiply. That's the same thing as multiplying the two vectors separately and then adding. Distributing over scalar addition, that means I can add two scalars and multiply, and that's the same thing as multiplying the scalars separately and adding. And then there's a one scalar. The one scalar times u is equal to u. All right, so these are all properties. You may seem that this goes over fairly quickly, but if you think about each property, it does make sense. And you might even wonder why we're talking about these properties. What we'll see is that there are other types of vectors besides C3 or C2 or Cn that also have these properties, and we'll see that in a little while. All right, these are all properties that can be derived from the definition. The zero vector is unique. Remember, the zero vector is a vector that add to any other vector gives the same vector. So remember that u plus 0 is equal to u. And what this is saying is that there's only one vector in the vector space that has this property for all u. Okay. And given any vector v, the additive inverse is unique, so that's kind of similar. The zero scalar times any vector will give you the zero vector. So understand what this is saying. This is a zero scalar. If I multiply any vector times the zero scalar, I get the zero vector. So think about that. If I have a vector in three-dimensional space and I multiply that by 0, the result has length 0, so it's a zero vector. Similarly, any scalar multiple times the zero vector is the zero vector. That also makes sense. If I have the zero vector, which I could represent by a point, if I multiply that by any scalar, if I scale that point, it's just going to stay a point. All right, this is what I referred to earlier, that the additive inverse of a vector is actually minus 1 times that vector. And then this is a property we've seen in other contexts, that if you have a scalar multiple times a vector, and that's equal to the zero vector, then either the scalar is 0 or the vector is 0. Now, the first group of exercises that I want to look at are this type of exercise where you have a different set or different vector operation from what you're used to, and you want to see if that's actually a vector space. Okay, so here we're talking about a new vector space that we haven't seen before, or actually I should say rather a new scalar multiplication operation that we haven't seen before. And we want to see if the usual set of vectors with this new scalar multiplication still satisfies the condition of a vector space. Right? So don't be confused here. We're not talking about regular, well, in a way we're talking about regular vectors, but we're talking about a different scalar operation. So really this is a new type of object where we multiply the vector and get a different type of result than what we're used to. So in this case, in this set here, we're saying v has the usual vector addition. Then we're redefining scalar multiplication in this way, that alpha times the vector is equal to alpha times the vector components in the reverse order. So for instance, if I had 3 times 1, 2, that would be equal to, you can see the definition here, 3 is my alpha, x is 1, y is 2, so this would be alpha y, this would be equal to 3 times 2, or 3 times 1. Okay, or 6, 3. Now that's different from the usual scalar multiplication where you'd have 3, 6. So we're talking about a new type of multiplication operation. So we want to see if this new type of multiplication operation actually still gives me a vector space. So what you want to do is go through all of the properties that are here and make sure that they're all satisfied. Now because the vector addition hasn't changed, then you expect all of the additive properties still to be true, because we're still using the regular vector addition. So we should look at the multiplicative properties and see if those are still true. Well, if you look at scalar closure, it's still true, according to this definition, that the scalar multiple of a vector is still a vector. So the scalar multiple property is still true. Now, as I said, this is an additive property, this is an additive property. Now, zero vector, this is an additive property, so we can skip that. Additive inverse, that's additive property. Let's look at this one. Scalar multiplicative associativity. So let's see if this is still true. What this says is that if I multiply a vector times a constant, then multiply by another constant, that's the same thing as multiplying the constants together and getting a vector. Now let's see if that equation holds in our new vector space with our new scalar multiplication. So let's try to verify this equation. So let's say u is xy, and we multiply first by beta and then by alpha. So if we want to take alpha of beta mu, but now beta u, according to this definition, is going to be beta y, beta x, right? Beta u is like alpha here, except instead of multiplying by alpha, we're multiplying by beta. So we get beta y, beta x here. Now if we multiply that by alpha, what does that become? Remember what happens when you do scalar multiplication. When you do scalar multiplication, you take alpha times the bottom one here, and that becomes the top in the final result, and alpha times the top here, and that becomes the final result on the bottom. So this would be the final result of alpha times beta mu. All right, so let's look at the final result if we take alpha beta times u. Well, then alpha beta is our scalar. We multiply xy by alpha beta, and when we multiply a vector by a scalar, what we do is we multiply the different components by the scalar, but we reverse the components. So this would be alpha beta y, alpha beta x. All right. So in fact, you can see that these will not be equal in general. It would be good to give an example. You could say, for instance, very simple example, you could say alpha equals beta equals 1, and then you could say x equals 1, y equals 2. So in this case, if we have 1 times u, that's going to be equal to, according to this, it's going to be 1 times x, and 1 times 1 times 1, and this will be 1 times 2. Okay. On the other hand, if we do 1 times 1 times u, that's going to be equal to 1 times 2, and 1 times 1. So those are not equal to each other. Okay. It's always good to come up with a specific example that shows that you have a counterexample. So this is acceptable. I would say that this is a little bit better. Okay. So let's go on to the next one. Next one says, here we have a set C2. So this is regular two-component vectors with the usual scalar multiplication, but you redefine the addition. Let me view this. Let me zoom in a little bit. Okay. So here's our new vector addition. If I add xy plus zw, it's a kind of a similar definition. Instead of adding the components directly, I add the components and then flip the components. So the second component of my result is x plus z. First component is y plus w. So this is a new type of addition that we haven't seen before, and we want to see if this still gives me a vector space. All right. So let's go ahead and see if all the properties are satisfied. Now, one of those properties is associative property. You can go through and look at this and see that when I do this, I get two different answers. If I take xy plus parenthesis ZW plus PQ. If I work that through, I get this: y plus Z plus P, X plus Y plus X plus W plus Q. If instead I take the other way, then I'll get X plus Z plus Q and Y. I think I made a mistake. Yeah, X plus Z plus Q, Y plus W plus P. So again, we could give a particular example. We could say X equals 1, Y equals 0, and then we could let all the others be 0. Z equals W equals P equals Q is equal to 0. In that case, we're going, according to this formula, we have 1, 0 plus 0, 0, and that's going to be plus 0, 0. According to this formula, that's going to give me X plus Z plus Q, so that's going to be 1 on the top, and then it's 0 on the bottom. On the other hand, if I take, did I make a mistake here? I should have been up here, sorry. No, that's right. This one corresponds to this one here. On the other hand, but if we look at the top formula here, if we have 1, 0 plus 0, 0 plus 0, 0, if you work out the formula, that's going to give me equal to 0, 1. All right, now, I should mention that we found that this associative property doesn't hold. If you work through the properties, you could probably find some other property that doesn't hold. But you just need to find one property that doesn't hold, and this means that it's not a vector space. Okay. So there are other problems in the book where this is done, so you should practice those other problems. And I'm going to stop here, and we'll look at the other properties in a different video.